Welcome to our 2FH3 project proposal. Our project is based upon the electromagnetic structure of an antenna, specifically a horn antenna. But what is a horn antenna? A horn antenna or a microwave antenna is used to transmit waves, specifically radio waves, from a waveguide into a beam. A waveguide is a structure that guides waves such as electromagnetic waves or sound. Waveguides allow for low loss energy transfer. As you can see, the waveguide is connected to the backside of the horn. This is done by having one dimension of its wall greater than half the wavelength, which allows for minimal loss. The horn antenna signal is transmitted into the waveguide through a coaxial cable. As you can see right here, this is the input for the coaxial cable, which is then transmitted through a center conductor projecting into the waveguide, and this forms a monopole antenna, thus transmitting the signal into the flaring region. As you can see, the horn is flared in the X, Y, and Z direction. The horn antenna operates at microwave frequencies above 300 megahertz. As you can see right here, here's the spectrum here's the electromagnetic spectrum, and we have radio waves right here. Typically, the horn antenna operates above the radio waves. As you may be able to tell, the horn antenna is basically a waveguide which flares out. This is because the horn antenna acts as an impedance matcher between the waveguide and free space. By having a tapered or having a flared end to the waveguide, the horn antenna is formed, and this enables the impedance of free space to be matched. Although the waveguide will radiate without the horn antenna, this provides a far more efficient match. The main advantage of the horn antenna is that it provides a significant level of directivity and gain. However, due to its dependence on geometry, this can be seen as a disadvantage because now the flare angle is decided, which in turn sets the directivity permanently. Here are some applications of the horn antenna. Typically used as feed antenna, the horn antenna provides for large antenna structures such as parabolic antennas. Since antennas both transmit and receive signals, the horn antenna can also receive signals. But here is an image of a communications satellite, and the horn antenna is usually used in transmitters where they usually feed the signal into a communications satellite. Horn antennas are commonly used as the active element in a dish antenna. The horn antenna is pointed towards the center of the dish reflector. The use of the horn rather than a dipole antenna or any other type of antenna at the focal point of the dish minimizes loss of energy around the edges of the dish reflector. It also minimizes the response of the antenna to unwanted signals not in the favored direction of the dish.
Now we'll be discussing the geometry of horn antennas. The generic horn antenna was given its name due to its flaring horn-like topology attached to the end of a narrow waveguide. Horn antennas can have various geometric shapes, each with their own distinct properties. However, they all maintain a horn-like contour, as you can see here with these applications. Now, the exponential horn, also known as the scalar horn antenna, combines its narrow waveguide with the horn in a smooth curve-like fashion, as you can see in this basic shape here. This allows for greatly reduced internal reflections and almost a constant impedance over a wide frequency range. These antennas are usually utilized in applications requiring high performance, such as communication satellites or radio telescopes. Now, the conical horn antenna is similar to the exponential one. However, instead of a curve representation, there is a cone, or a conical shape, attached to a cylindrical one. This type of antenna is good for high bandwidth and stable performance over wide ranges of frequencies. Although the antenna is good for many characteristics, other types of antennas beat it in specific characteristics, meaning this one isn't really used over other antennas. The E and H-plane horn antennas contain a flat rectangular waveguide attached to a rectangular horn of the same constant width or length. These flares expand towards the direction of the electric field. The E field determines the polarization/orientation of the radio wave, meaning the vertical/horizontal planes you would use for any applications. So as you can see, the E antenna is used for mostly vertical planes. Finally, the pyramidal, or specifically the antenna we will be focusing on in this project, horn antenna, this is the most common antenna, distinguished by its rectangular cross-section flare attached to a rectangular waveguide. They radiate linearly polarized radio waves. An example would be like microwaves. Due to its high bandwidth, this antenna makes a great resonator for microwaves, Although the performance may vary over a wide frequency range, this antenna still makes for a good traffic control, such as guns.
As learned from previous slides, the horn antenna has flaring. The flaring of the horn helps to match the antenna impedance to the impedance of free space for a better radiation. The flare angle theta of the horn antenna is an important factor to be considered. If this angle is too small, then the resulting wave will be spherical instead of plane, and the radiated beam will not be directive. Hence, the flare angle should be optimum value and closely related to its length.
The basic theory of a horn antenna is as such. The waves of the signal will propagate down the horn antenna towards the aperture. As they travel along the flared opening, the waves travel as spherical wavefronts, having their apex at the apex of the horn. The apex is basically a point referred to as the phase center of the horn antenna. Since the phase fronts progressing along the horn antenna are spherical, the phase increases smoothly from the edges of the aperture to the center. The theory dictates that as the frequency used by the horn antenna increases, so does the gain and directivity. The reason for this is that the aperture of the horn remains constant in terms of physical dimensions, but increases in terms of wavelength. Antennas tend to have higher gain levels as they become larger, so it can be intuitively seen that the gain and directivity of the horn antenna will increase with frequency. Gain and directivity are shown in the following formulas.
A standard horn antenna is usually made with metal as the primary material. Metals usually chosen as they are conductive and malleable, thus making it easier to form the shape of the antenna. This is the norm, but theoretically any conductive material can be used to make an antenna. For example, there are papers concerning using graphene-based antenna formation. Due to its cheaper case and wider availability, metals remain the norm, however.
OpenEMS is an open source addition to MATLAB, which allows the simulation and calculation for a variety of electromagnetic objects. The following code comes from a tutorial for a rectangular horn antenna. This section of the code sets up the basic values for the simulation, such as dimensions and frequency. Specifically, the dimension of the horn of the antenna, the size of the simulation region, and the frequencies of interest. This antenna is designed to work within the range of 10 GHz and 20 GHz, averaging out to 15 GHz. This section of the code sets the parameters for the finite difference time domain method. It calls the CSX library, which is a C++ library concerning shape-based object creation and orientation. This is needed for the creation of the mesh, which facilitates the FDTD method and the horn itself. These pieces of code create the aforementioned horn using the CSX library. It creates the structure of the horn, which can be seen on the right. The following 6 sections of code perform these actions respectively. Firstly, it creates an application of the excitation function. In other words, the wave the antenna will be generating or receiving. Then it creates a basis for the calculations of wave interpretation, which will come later in the OpenEMS code. Then it creates the folders, which will store and run the simulation. Then there is the creation of the file compatible with OpenEMS itself. Then there is creation and display of the structure of the horn antenna, which was seen earlier. Lastly, it makes the calculations using the OpenEMS software. These sections take the data from the OpenEMS software and display it in a form of plots we can understand. The first section performs post-processing of the data for wave frequency against reflection coefficient in a logarithmic manner similar to decibels. The second calculates the electromagnetic field directly in comparison to the effectiveness of the horn, also displayed in a logarithmic manner. These sections calculate and display other datasets taken from the simulation, such as the directivity and the 3D pattern of the resulting wave. In order to adapt this OpenEMS structure for our chosen paper, we must modify its geometric structure from that of a basic rectangular horn antenna to the one shown below for approved effectiveness at specific frequencies. This concludes our presentation on horn antennas. We thank you for taking the time to view it.